All right, you can imagine this being applied to many sorts of different deductive situations. So not only these situations where we're trying to deal with Harry Potter characters in this puzzle, but if you've ever played games like Mastermind, where you're trying to figure out which order different colors go in and trying to make predictions about it, I could tell you, for example, let's play a simplified version of Mastermind where there are 4 colors, red, blue, green, and yellow, and they're in some order, but I'm not telling you what order. You just have to make a guess, and I'll tell you of red, blue, green, and yellow how many of the 4 you got in the right position. So a simplified version of this game, you might make a guess like red, blue, green, yellow, and I would tell you something like 2 of those 4 are in the correct position, but the other 2 are not. Then you could reasonably make a guess and say, all right, let's try this. Blue, red, green, yellow. Try switching 2 of them around. And this time, maybe I tell you, you know what? None of those are in the correct position. And the question then is, all right, what is the correct order of these 4 colors? And we as humans could begin to reason this through. All right, well, if none of these were correct, but 2 of these were correct, well, it must have been because I switched the red and the blue, which means red and blue here must be correct, which means green and yellow are probably not correct. You can begin to do this sort of deductive reasoning. We can also equivalently try and take this and encode it inside of our computer as well. And it's going to be very similar to the logic puzzle that we just did a moment ago. So I won't spend too much time on this code because it is fairly similar. But again, we have a whole bunch of colors and 4 different positions in which those colors can be. And then we have some additional knowledge. And I encode all of that knowledge. And you can take a look at this code on your own time. But I just want to demonstrate that when we run this code, run python mastermind.py, and run and see what we get, we ultimately are able to compute red 0 in the 0 position, blue in the 1 position, yellow in the 2 position, and green in the 3 position as the ordering of those symbols. Now, ultimately, what you might have noticed is this process was taking quite a long time. And in fact, model checking is not a particularly efficient algorithm, right? What I need to do in order to model check is take all of my possible different variables and enumerate all of the possibilities that they could be in. If I have n variables, I have 2 to the n possible worlds that I need to be looking through in order to perform this model checking algorithm. And this is probably not tractable, especially as we start to get to much larger and larger sets of data where you have many, many more variables that are at play. Right here, we only have a relatively small number of variables, so this sort of approach can actually work. But as the number of variables increases, model checking becomes less and less good of a way of trying to solve these sorts of problems. So while it might have been OK for something like Mastermind to conclude that this is indeed the correct sequence where all 4 are in the correct position, what we'd like to do is come up with some better ways to be able to make inferences rather than just enumerate all of the possibilities. And to do so, what we'll transition to next is the idea of inference rules, some sort of rules that we can apply to take knowledge that already exists and translate it into new forms of knowledge. And the general way we'll structure an inference rule is by having a horizontal line here. Anything above the line is going to represent a premise, something that we know to be true. And then anything below the line will be the conclusion that we can arrive at after we apply the logic from the inference rule that we're going to demonstrate. So we'll do some of these inference rules by demonstrating them in English first, but then translating them into the world of propositional logic so you can see what those inference rules actually look like. So for example, let's imagine that I have access to 2 pieces of information. I know, for example, that if it is raining, then Harry is inside, for example. And let's say I also know it is raining. Then most of us could reasonably then look at this information and conclude that, all right, Harry must be inside. This inference rule is known as modus ponens, and it's phrased more formally in logic as this. If we know that alpha implies beta, in other words, if alpha, then beta, and we also know that alpha is true, then we should be able to conclude that beta is also true. We can apply this inference rule to take these 2 pieces of information and generate this new piece of information. Notice that this is a totally different approach from the model checking approach, where the approach was look at all of the possible worlds and see what's true in each of these worlds. Here, we're not dealing with any specific world. We're just dealing with the knowledge that we know and what conclusions we can arrive at based on that knowledge. That I know that A implies B, and I know A, and the conclusion is B. And this should seem like a relatively obvious rule, that of course, if alpha, then beta, and we know alpha, then we should be able to conclude that beta is also true. And that's going to be true for many, but maybe even all, of the inference rules that we'll take a look at. You should be able to look at them and say, yeah, of course that's going to be true. But it's putting these all together, figuring out the right combination of inference rules that can be applied that ultimately is going to allow us to generate interesting knowledge inside of our AI. So that's modus ponens, this application of implication, that if we know alpha and we know that alpha implies beta, then we can conclude beta. Let's take a look at another example. Fairly straightforward, something like Harry is friends with Ron and Hermione. Based on that information, we can reasonably conclude Harry is friends with Hermione. That must also be true. And this inference rule is known as and elimination. And what and elimination says is that if we have a situation where alpha and beta are both true, I have information alpha and beta, well then, just alpha is true. Or likewise, just beta is true. That if I know that both parts are true, then one of those parts must also be true. Again, something obvious from the point of view of human intuition, but a computer needs to be told this kind of information. To be able to apply the inference rule, we need to tell the computer that this is an inference rule that you can apply, so the computer has access to it and is able to use it in order to translate information from one form to another. In addition to that, let's take a look at another example of an inference rule. Something like, it is not true that Harry did not pass the test. Bit of a tricky sentence to parse. I'll read it again. It is not true, or it is false, that Harry did not pass the test. Well, if it is false that Harry did not pass the test, then the only reasonable conclusion is that Harry did pass the test. And so this, instead of being and elimination, is what we call double negation elimination. That if we have two negatives inside of our premise, then we can just remove them altogether. They cancel each other out. One turns true to false, and the other one turns false back into true. Phrased a little bit more formally, we say that if the premise is not alpha, then the conclusion we can draw is just alpha. We can say that alpha is true. We'll take a look at a couple more of these. If I have it is raining, then Harry is inside. How do I reframe this? Well, this one is a little bit trickier. But if I know if it is raining, then Harry is inside, then I conclude one of two things must be true. Either it is not raining, or Harry is inside. Now this one's trickier, so let's think about it a little bit. This first premise here, if it is raining, then Harry is inside, is saying that if I know that it is raining, then Harry must be inside. So what is the other possible case? Well, if Harry is not inside, then I know that it must not be raining. So one of those two situations must be true. Either it's not raining, or it is raining, in which case Harry is inside. So the conclusion I can draw is either it is not raining, or it is raining, so therefore Harry is inside. And so this is a way to translate if-then statements into or statements. And this is known as implication elimination. And this is similar to what we actually did in the beginning when we were first looking at those very first sentences about Harry and Hagrid and Dumbledore. And phrased a little bit more formally, this says that if I have the implication alpha implies beta, that I can draw the conclusion that either not alpha or beta. Because there are only two possibilities. Either alpha is true or alpha is not true. So one of those possibilities is alpha is not true. But if alpha is true, well, then we can draw the conclusion that beta must be true. So either alpha is not true, or alpha is true, in which case beta is also true. So this is one way to turn an implication into just a statement about or. In addition to eliminating implications, we can also eliminate biconditionals as well. So let's take an English example, something like, it is raining if and only if Harry is inside. And this if and only if really sounds like that biconditional, that double arrow sign that we saw in propositional logic not too long ago. And what does this actually mean if we were to translate this? Well, this means that if it is raining, then Harry is inside. And if Harry is inside, then it is raining. That this implication goes both ways. And this is what we would call biconditional elimination. That I can take a biconditional, A if and only if B, and translate that into something like this. A implies B, and B implies A. So many of these inference rules are taking logic that uses certain symbols and turning them into different symbols, taking an implication and turning it into an or taking a biconditional and turning it into implication. And another example of it would be something like this. It is not true that both Harry and Ron passed the test. Well, all right, how do we translate that? What does that mean? Well, if it is not true that both of them passed the test, well, then the reasonable conclusion we might draw is that at least one of them didn't pass the test. So the conclusion is either Harry did not pass the test or Ron did not pass the test, or both. This is not an exclusive or. But if it is true that it is not true that both Harry and Ron passed the test, well, then either Harry didn't pass the test or Ron didn't pass the test. And this type of law is one of De Morgan's laws, quite famous in logic, where the idea is that we can turn an and into an or. We can take this and, that both Harry and Ron passed the test, and turn it into an or by moving the nots around. So if it is not true that Harry and Ron passed the test, well, then either Harry did not pass the test or Ron did not pass the test either. And the way we frame that more formally using logic is to say this. If it is not true that alpha and beta, well then, either not alpha or not beta. The way I like to think about this is that if you have a negation in front of an and expression, you move the negation inwards, so to speak, moving the negation into each of these individual sentences, and then flip the and into an or. So the negation moves inwards, and the and flips into an or. So I go from not A and B to not A or not B. And there's actually a reverse of De Morgan's law that goes in the other direction for something like this. If I say, it is not true that Harry or Ron passed the test, meaning neither of them passed the test, well, then the conclusion I can draw is that Harry did not pass the test and Ron did not pass the test. So in this case, instead of turning an and into an or, we're turning an or into an and. But the idea is the same. And this, again, is another example of De Morgan's laws. And the way that works is that if I have not A or B this time, the same logic's going to apply. I'm going to move the negation inwards, and I'm going to flip the or into an and. So if not A or B, meaning it is not true that A or B, or alpha or beta, then I can say not alpha and not beta, moving the negation inwards in order to make that conclusion. So those are De Morgan's laws, and a couple other inference rules that are worth just taking a look at. One is the distributive law that works this way. So if I have alpha and beta or gamma, well then, much in the same way that you can use in math, use distributive laws to distribute operands like addition and multiplication, I can do a similar thing here, where I can say if alpha and beta or gamma, then I can say something like alpha and beta or alpha and gamma, that I've been able to distribute this and sign throughout this expression. So this is an example of the distributive property or the distributive law as applied to logic in much the same way that you would distribute like a multiplication over the addition of something, for example. This works the other way too. So if, for example, I have alpha or beta and gamma, I can distribute the or throughout the expression. I can say alpha or beta and alpha or gamma. So the distributive law works in that way too, and it's helpful if I want to take an or and move it into the expression. And we'll see an example soon of why it is that we might actually care to do something like that. All right, so now we've seen a lot of different inference rules. And the question now is, how can we use those inference rules to actually try and draw some conclusions, to actually try and prove something about entailment, proving that given some initial knowledge base, we would like to find some way to prove that a query is true? Well, one way to think about it is actually to think back to what we talked about last time, when we talked about search problems. Recall again that search problems have some sort of initial state. They have actions that you can take from one state to another, as defined by a transition model that tells you how to get from one state to another. We talked about testing to see if you're at a goal, and then some path cost function to see how many steps did you have to take, or how costly was the solution that you found. Now that we have these inference rules that take some set of sentences in propositional logic and get us some new set of sentences in propositional logic, we can actually treat those sentences, or those sets of sentences, as states inside of a search problem. So if we want to prove that some query is true, prove that some logical theorem is true, we can treat theorem proving as a form of a search problem. I can say that we begin in some initial state, where that initial state is the knowledge base that I begin with, the set of all of the sentences that I know to be true. What actions are available to me? Well, the actions are any of the inference rules that I can apply at any given time. The transition model just tells me, after I apply the inference rule, here is the new set of all of the knowledge that I have, which will be the old set of knowledge, plus some additional inference that I've been able to draw, much as in the same way we saw what we got when we applied those inference rules and got some sort of conclusion. That conclusion gets added to our knowledge base, and our transition model will encode that. What is the goal test? Well, our goal test is, checking to see if we have proved the statement we're trying to prove, if the thing we're trying to prove is inside of our knowledge base. And the path cost function, the thing we're trying to minimize, is maybe the number of inference rules that we needed to use, the number of steps, so to speak, inside of our proof. And so here we've been able to apply the same types of ideas that we saw last time with search problems to something like trying to prove something about knowledge by taking our knowledge and framing it in terms that we can understand as a search problem, with an initial state, with actions, with a transition model. So this shows up a couple of things. One being how versatile search problems are, that they can be the same types of algorithms that we use to solve a maze or figure out how to get from point A to point B inside of driving directions, for example, can also be used as a theorem proving method of taking some sort of starting knowledge base and trying to prove something about that knowledge. So this, yet again, is a second way, in addition to model checking, to try and prove that certain statements are true. But it turns out there's yet another way that we can try and apply inference, and we'll talk about this now, which is not the only way, but certainly one of the most common, which is known as resolution. And resolution is based on another inference rule that we'll take a look at now, quite a powerful inference rule that will let us prove anything that can be proven about a knowledge base. And it's based on this basic idea. Let's say I know that either Ron is in the Great Hall or Hermione is in the library. And let's say I also know that Ron is not in the Great Hall. Based on those two pieces of information, what can I conclude? Well, I could pretty reasonably conclude that Hermione must be in the library. How do I know that? Well, it's because these two statements, these two what we'll call complementary literals, literals that complement each other, they're opposites of each other, seem to conflict with each other. This sentence tells us that either Ron is in the Great Hall or Hermione is in the library. So if we know that Ron is not in the Great Hall, that conflicts with this one, which means Hermione must be in the library. And this we can frame as a more general rule known as the unit resolution rule, a rule that says that if we have P or Q, and we also know not P, well, then from that we can reasonably conclude Q. That if P or Q are true, and we know that P is not true, the only possibility is for Q to then be true. And this, it turns out, is quite a powerful inference rule in terms of what it can do, in part because we can quickly start to generalize this rule. This Q right here doesn't need to just be a single propositional symbol. It could be multiple, all chained together in a single clause, as we'll call it. So if I had something like P or Q1 or Q2 or Q3, so on and so forth, up until Qn, so I had n different other variables, and I have not P, well, then what happens when these two complement each other is that these two clauses resolve, so to speak, to produce a new clause that is just Q1 or Q2 all the way up to Qn. And in an OR, the order of the arguments in the OR doesn't actually matter. The P doesn't need to be the first thing. It could have been in the middle. But the idea here is that if I have P in one clause and not P in the other clause, well, then I know that one of these remaining things must be true. I've resolved them in order to produce a new clause. But it turns out we can generalize this idea even further, in fact, and display even more power that we can have with this resolution rule. So let's take another example. Let's say, for instance, that I know the same piece of information, that either Ron is in the Great Hall or Hermione is in the library. And the second piece of information I know is that Ron is not in the Great Hall or Harry is sleeping. So it's not just a single piece of information. I have two different clauses, and we'll define clauses more precisely in just a moment. What do I know here? Well, again, for any propositional symbol, like Ron is in the Great Hall, there are only two possibilities. Either Ron is in the Great Hall, in which case, based on resolution, we know that Harry must be sleeping, or Ron is not in the Great Hall, in which case we know, based on the same rule, that Hermione must be in the library. Based on those two things in combination, I can say, based on these two premises, that I can conclude that either Hermione is in the library or Harry is sleeping. So again, because these two conflict with each other, I know that one of these two must be true. And you can take a closer look and try and reason through that logic. Make sure you convince yourself that you believe this conclusion. Stated more generally, we can name this resolution rule by saying that if we know P or Q is true, and we also know that not P or R is true, we resolve these two clauses together to get a new clause, Q or R, that either Q or R must be true. And again, much as in the last case, Q and R don't need to just be single propositional symbols. It could be multiple symbols. So if I had a rule that had P or Q1 or Q2 or Q3, so on and so forth, up until Qn, where n is just some number, and likewise, I had not P or R1 or R2, so on and so forth, up until Rm, where m, again, is just some other number, I can resolve these two clauses together to get one of these must be true, Q1 or Q2 up until Qn, or R1 or R2 up until Rm. And this is just a generalization of that same rule we saw before. Each of these things here are what we're going to call a clause, where a clause is formally defined as a disjunction of literals, where a disjunction means it's a bunch of things that are connected with or. Disjunction means things connected with or. Conjunction, meanwhile, is things connected with and. And a literal is either a propositional symbol or the opposite of a propositional symbol. So it's something like P or Q or not P or not Q. Those are all propositional symbols or not of the propositional symbols, and we call those literals. So a clause is just something like this, P or Q or R, for example. Meanwhile, what this gives us an ability to do is it gives us an ability to turn logic, any logical sentence, into something called conjunctive normal form. A conjunctive normal form sentence is a logical sentence that is a conjunction of clauses. Recall again, conjunction means things are connected to one another using and. And so a conjunction of clauses means that it is an and of individual clauses, each of which has ors in it. So something like this, A or B or C, and D or not E, and F or G. Everything in parentheses is one clause. All of the clauses are connected to each other using an and everything in the clause is separated using an or. And this is just a standard form that we can translate a logical sentence into that just makes it easy to work with and easy to manipulate. And it turns out that we can take any sentence in logic and turn it into conjunctive normal form just by applying some inference rules and transformations to it. So we'll take a look at how we can actually do that. So what is the process for taking a logical formula and converting it into conjunctive normal form, otherwise known as CNF? Well, the process looks a little something like this. We need to take all of the symbols that are not part of conjunctive normal form, the biconditionals and the implications and so forth, and turn them into something that is more closely like conjunctive normal form. So the first step will be to eliminate biconditionals, those if and only if double arrows. And we know how to eliminate biconditionals because we saw there was an inference rule to do just that. Anytime I have an expression like alpha if and only if beta, I can turn that into alpha implies beta and beta implies alpha, based on that inference rule we saw before. Likewise, in addition to eliminating biconditionals, I can eliminate implications as well, the if-then arrows. And I can do that using the same inference rule we saw before too, taking alpha implies beta and turning that into not alpha or beta, because that is logically equivalent to this first thing here. Then we can move knots inwards, because we don't want knots on the outsides of our expressions. Conjunctive normal form requires that it's just clause and clause and clause and clause. Any knots need to be immediately next to propositional symbols. But we can move those knots around using De Morgan's laws by taking something like not A and B and turn it into not A or not B, for example, using De Morgan's laws to manipulate that. And after that, all we'll be left with are ands and ors, and those are easy to deal with. We can use the distributive law to distribute the ors so that the ors end up on the inside of the expression, so to speak, and the ands end up on the outside. So this is the general pattern for how we'll take a formula and convert it into conjunctive normal form. And let's now take a look at an example of how we would do this and explore then why it is that we would want to do something like this. Here's how we can do it. Let's take this formula, for example. P or Q implies R, and I'd like to convert this into conjunctive normal form. where it's all ands of clauses, and every clause is a disjunctive clause. It's ors together. So what's the first thing I need to do? Well, this is an implication, so let me go ahead and remove that implication. Using the implication inference rule, I can turn P or Q into P or Q implies R into not P or Q or R. So that's the first step. I've gotten rid of the implication. And next, I can get rid of the not on the outside of this expression, too. I can move the nots inwards so they're closer to the literals themselves by using De Morgan's laws. And De Morgan's law says that not P or Q is equivalent to not P and not Q. Again, here, just applying the inference rules that we've already seen in order to translate these statements. And now I have two things that are separated by an or, where this thing on the inside is an and. What I'd really like is to move the ors so the ors are on the inside, because conjunctive normal form means I need clause and clause and clause and clause. And so to do that, I can use the distributive law. If I have not P and not Q, or R, I can distribute the or R to both of these to get not P or R and not Q or R using the distributive law. And this now here at the bottom is in conjunctive normal form. It is a conjunction, an and, of disjunctions of clauses that just are separated by ors. And so this process can be used by any formula to take a logical sentence and turn it into this conjunctive normal form where I have clause and clause and clause and clause and clause and so on. So why is this helpful? Why do we even care about taking all these sentences and converting them into this form? It's because once they're in this form where we have these clauses are the inputs to the resolution inference rule that we saw a moment ago. That if I have two clauses where there's something that conflicts or something complementary between those two clauses, I can resolve them to get a new clause, to draw a new conclusion. And we call this process inference by resolution, using the resolution rule to draw some sort of inference. And it's based on the same idea, that if I have P or Q, this clause, and I have not P or R, that I can resolve these two clauses together to get Q or R as the resulting clause, a new piece of information that I didn't have before. Now, a couple of key points that are worth noting about this before we talk about the actual algorithm. One thing is that let's imagine we have P or Q or S, and I also have not P or R or S. The resolution rule says that because this P conflicts with this not P, we would resolve to put everything else together to get Q or S or R or S. But it turns out that this double S is redundant, or S here and or S there. It doesn't change the meaning of the sentence. So in resolution, when we do this resolution process, we'll usually also do a process known as factoring, where we take any duplicate variables that show up and just eliminate them. So Q or S or R or S just becomes Q or R or S. The S only needs to appear once, no need to include it multiple times. Now, one final question worth considering is what happens if I try to resolve P and not P together? If I know that P is true and I know that not P is true, well, resolution says I can merge these clauses together and look at everything else. Well, in this case, there is nothing else, so I'm left with what we might call the empty clause. I'm left with nothing. And the empty clause is always false. The empty clause is equivalent to just being false. And that's pretty reasonable, because it's impossible for both P and not P to both hold at the same time. P is either true or it's not true, which means that if P is true, then this must be false. And if this is true, then this must be false. There's no way for both of these to hold at the same time. So if ever I try and resolve these two, it's a contradiction, and I'll end up getting this empty clause, where the empty clause I can call equivalent to false. And this idea that if I resolve these two contradictory terms, I get the empty clause, this is the basis for our inference by resolution algorithm. Here's how we're going to perform inference by resolution at a very high level. We want to prove that our knowledge base entails some query alpha, that based on the knowledge we have, we can prove conclusively that alpha is going to be true. How are we going to do that? Well, in order to do that, we're going to try to prove that if we know the knowledge and not alpha, that would be a contradiction. And this is a common technique in computer science more generally, this idea of proving something by contradiction. If I want to prove that something is true, I can do so by first assuming that it is false and showing that it would be contradictory. showing that it leads to some contradiction. And if the thing I'm trying to prove, if when I assume it's false, leads to a contradiction, then it must be true. And that's the logical approach or the idea behind a proof by contradiction. And that's what we're going to do here. We want to prove that this query alpha is true. So we're going to assume that it's not true. We're going to assume not alpha. And we're going to try and prove that it's a contradiction. If we do get a contradiction, well, then we know that our knowledge entails the query alpha. If we don't get a contradiction, there is no entailment. This is this idea of a proof by contradiction, of assuming the opposite of what you're trying to prove. And if you can demonstrate that that's a contradiction, then what you're proving must be true. But more formally, how do we actually do this? How do we check that knowledge base and not alpha is going to lead to a contradiction? Well, here's where resolution comes into play. To determine if our knowledge base entails some query alpha, we're going to convert knowledge base and not alpha to conjunctive normal form, that form where we have a whole bunch of clauses that are all anded together. And when we have these individual clauses, now we can keep checking to see if we can use resolution to produce a new clause. Right? We can take any pair of clauses and check, is there some literal that is the opposite of each other or complementary to each other in both of them? For example, I have a p in one clause and a not p in another clause, or an r in one clause and a not r in another clause. If ever I have that situation where once I convert to conjunctive normal form and I have a whole bunch of clauses, I see two clauses that I can resolve to produce a new clause, then I'll do so. This process occurs in a loop. I'm going to keep checking to see if I can use resolution to produce a new clause and keep using those new clauses to try to generate more new clauses after that. Now, it just so may happen that eventually we may produce the empty clause, the clause we were talking about before. If I resolve p and not p together, that produces the empty clause. And the empty clause we know to be false, because we know that there's no way for both p and not p to both simultaneously be true. So if ever we produce the empty clause, then we have a contradiction. And if we have a contradiction, that's exactly what we were trying to do in a proof by contradiction. If we have a contradiction, then we know that our knowledge base must entail this query alpha. We know that alpha must be true. And it turns out, and we won't go into the proof here, but you can show that otherwise, if you don't produce the empty clause, then there is no entailment. If we run into a situation where there are no more new clauses to add, we've done all the resolution that we can do, and yet we still haven't produced the empty clause, then there is no entailment in this case. And this now is the resolution algorithm. And it's very abstract looking, especially this idea of like, what does it even mean to have the empty clause? So let's take a look at an example. Actually try and prove some entailment by using this inference by resolution process. So here's our question. We have this knowledge base. Here's the knowledge that we know, A or B, and not B or C, and not C. And we want to know if all of this entails A. So this is our knowledge base here, this whole long thing. And our query alpha is just this propositional symbol A. So what do? Well, first, we want to prove by contradiction. So we want to first assume that A is false and see if that leads to some sort of contradiction. So here's what we're going to start with, A or B, and not B or C, and not C. This is our knowledge base. And we're going to assume not A. We're going to assume that the thing we're trying to prove is, in fact, false. And so this is now in conjunctive normal form. And I have 4 different clauses. I have A or B. I have not B or C. I have not C. And I have not A. And now I can begin to just pick 2 clauses that I can resolve and apply the resolution rule to them. And so looking at these 4 clauses, I see, all right, these 2 clauses are ones I can resolve. I can resolve them because there are complementary literals that show up in them. There's a C here and a not C here. So just looking at these 2 clauses, if I know that not B or C is true, and I know that C is not true, well, then I can resolve these 2 clauses to say, all right, not B, that must be true. I can generate this new clause as a new piece of information that I now know to be true. And all right, now I can repeat this process, do the process again. Can I use resolution again to get some new conclusion? Well, it turns out I can. I can use that new clause I just generated along with this one here. There are complementary literals. This B is complementary to, or conflicts with, this not B over here. And so if I know that A or B is true, and I know that B is not true, well, then the only remaining possibility is that A must be true. So now we have A. That is a new clause that I've been able to generate. And now I can do this one more time. I'm looking for two clauses that can be resolved. And you might programmatically do this by just looping over all possible pairs of clauses and checking for complementary literals in each. And here I can say, all right, I found two clauses, not A and A, that conflict with each other. And when I resolve these two together, well, this is the same as when we were resolving P and not P from before. When I resolve these two clauses together, I get rid of the A's, and I'm left with the empty clause. And the empty clause we know to be false, which means we have a contradiction, which means we can safely say that this whole knowledge base does entail A. That if this sentence is true, that we know that A for sure is also true. So this now, using inference by resolution, is an entirely different way to take some statement and try and prove that it is in fact true. Instead of enumerating all of the possible worlds that we might be in order to try to figure out in which cases is the knowledge base true and in which cases our query true, instead we use this resolution algorithm to say, let's keep trying to figure out what conclusions we can draw and see if we reach a contradiction. And if we reach a contradiction, then that tells us something about whether our knowledge actually entails the query or not. And it turns out there are many different algorithms that can be used for inference. What we've just looked at here are just a couple of them. And in fact, all of this is just based on one particular type of logic. It's based on propositional logic, where we have these individual symbols, and we connect them using and or and not and implies and biconditionals. But propositional logic is not the only kind of logic that exists. And in fact, we see that there are limitations that exist in propositional logic, especially as we saw in examples like with the mastermind example or with the example with the logic puzzle, where we had different Hogwarts house people that belonged to different houses, and we were trying to figure out who belonged to which houses. There were a lot of different propositional symbols that we needed in order to represent some fairly basic ideas. So now, as a final topic that we'll take a look at just before we end class today, is one final type of logic different from propositional logic, known as first-order logic, which is a little bit more powerful than propositional logic and is going to make it easier for us to express certain types of ideas. In propositional logic, if we think back to that puzzle with the people in the Hogwarts houses, we had a whole bunch of symbols, and every symbol could only be true or false, right? We had a symbol for Minerva Gryffindor, which was either true if Minerva was in Gryffindor and false otherwise, and likewise for Minerva Hufflepuff and Minerva Ravenclaw and Minerva Slytherin, and so forth. But this was starting to get quite redundant, that we wanted some way to be able to express that there's a relationship between these propositional symbols, that Minerva shows up in all of them. And also, I would have liked to not have had so many different symbols to represent what really was a fairly straightforward problem. So first-order logic will give us a different way of trying to deal with this idea by giving us two different types of symbols. We're going to have constant symbols that are going to represent objects like people or houses, and then predicate symbols, which you can think of as relations or functions that take an input and evaluate them to like true or false, for example, that tell us whether or not some property of some constant or some pair of constants or multiple constants actually holds. So we'll see an example of that in just a moment. But for now, in this same problem, our constant symbols might be objects, things like people or houses. So Minerva, Pomona, Horace, Gilderoy, those are all constant symbols, as are my four houses, Gryffindor, Hufflepuff, Ravenclaw, and Slytherin. Predicates, meanwhile, these predicate symbols are going to be properties that might hold true or false of these individual constants. So person might hold true of Minerva, but it would be false for Gryffindor, because Gryffindor is not a person. And house is going to hold true for Ravenclaw, but it's not going to hold true for Horace, for example, because Horace is a person. And belongs to, meanwhile, is going to be some relation that is going to relate people to their houses. And it's going to only tell me when someone belongs to a house or does not. So let's take a look at some examples of what a sentence in first-order logic might actually look like. A sentence might look like something like this: person Minerva, with Minerva in parentheses, and person being a predicate symbol, Minerva being a constant symbol. This sentence in first-order logic effectively means Minerva is a person, or the person property applies to the Minerva object. So if I want to say something like Minerva is a person, here is how I express that idea using first-order logic. Meanwhile, I can say something like house Gryffindor to likewise express the idea that Gryffindor is a house. I can do that this way. And all of the same logical connectives that we saw in propositional logic, those are going to work here too. So and, or, implication, biconditional, not. In fact, I can use not to say something like not house Minerva. And this sentence in first order logic means something like Minerva is not a house. It is not true that the house property applies to Minerva. Meanwhile, in addition to some of these predicate symbols that just take a single argument, some of our predicate symbols are going to express binary relations, relations between two of its arguments. So I could say something like belongs to, and then two inputs, Minerva and Gryffindor, to express the idea that Minerva belongs to Gryffindor. And so now here's the key difference, or one of the key differences between this and propositional logic. In propositional logic, I needed one symbol for Minerva Gryffindor, and one symbol for Minerva Hufflepuff, and one symbol for all the other people's Gryffindor and Hufflepuff variables. In this case, I just need one symbol for each of my people, and one symbol for each of my houses. And then I can express as a predicate something like belongs to, and say belongs to Minerva Gryffindor to express the idea that Minerva belongs to Gryffindor house. So already we can see that first order logic is quite expressive in being able to express these sorts of sentences using the existing constant symbols and predicates that already exist while minimizing the number of new symbols that I need to create. I can just use 8 symbols for people, for houses, instead of 16 symbols for every possible combination of each. But first order logic gives us a couple of additional features that we can use to express even more complex ideas. And these additional features are generally known as quantifiers. And there are two main quantifiers in first order logic, the first of which is universal quantification. Universal quantification lets me express an idea like something is going to be true for all values of a variable. Like for all values of x, some statement is going to hold true. So what might a sentence in universal quantification look like? Well, we're going to use this upside down a to mean for all. So upside down ax means for all values of x, where x is any object, this is going to hold true. Belongs to x Gryffindor implies not belongs to x Hufflepuff. So let's try and parse this out. This means that for all values of x, if this holds true, if x belongs to Gryffindor, then this does not hold true. X does not belong to Hufflepuff. So translated into English, this sentence is saying something like, for all objects x, if x belongs to Gryffindor, then x does not belong to Hufflepuff, for example. Or phrased even more simply, anyone in Gryffindor is not in Hufflepuff. Simplified way of saying the same thing. So this universal quantification lets us express an idea like something is going to hold true for all values of a particular variable. In addition to universal quantification, though, we also have existential quantification. Whereas universal quantification said that something is going to be true for all values of a variable, existential quantification says that some expression is going to be true for some value of a variable, at least one value of the variable. So let's take a look at a sample sentence using existential quantification. One such sentence looks like this. There exists an x. This backwards e stands for exists. And here we're saying there exists an x such that house x and belongs to Minerva x. In other words, there exists some object x where x is a house and Minerva belongs to x. Or phrased a little more succinctly in English, I'm here just saying Minerva belongs to a house. There's some object that is a house, and Minerva belongs to a house. And combining this universal and existential quantification, we can create far more sophisticated logical statements than we were able to just using propositional logic. I could combine these to say something like this. For all x, person x implies there exists a y such that house y and belongs to xy. All right, so a lot of stuff going on there, a lot of symbols. Let's try and parse it out and just understand what it's saying. Here we're saying that for all values of x, if x is a person, then this is true. So in other words, I'm saying for all people, and we call that person x, this statement is going to be true. What statement is true of all people? Well, there exists a y that is a house. So there exists some house, and x belongs to y. In other words, I'm saying that for all people out there, there exists some house such that X, the person, belongs to Y, the house. So phrased more succinctly, I'm saying that every person belongs to a house. That for all X, if X is a person, then there exists a house that X belongs to. And so we can now express a lot more powerful ideas using this idea now of first-order logic. And it turns out there are many other kinds of logic out there. There's second-order logic and other higher-order logic, each of which allows us to express more and more complex ideas. But all of it, in this case, is really in pursuit of the same goal, which is the representation of knowledge. We want our AI agents to be able to know information, to represent that information, whether that's using propositional logic or first-order logic or some other logic, and then be able to reason based on that, to be able to draw conclusions, make inferences, figure out whether there's some sort of entailment relationship, as by using some sort of inference algorithm, something like inference by resolution or model checking, or any number of these other algorithms that we can use in order to take information that we know and translate it to additional conclusions. So all of this has helped us to create AI that is able to represent information about what it knows and what it doesn't know. Next time, though, we'll take a look at how we can make our AI even more powerful by not just encoding information that we know for sure to be true and not to be true, but also to take a look at uncertainty, to look at what happens if AI thinks that something might be probable or maybe not very probable or somewhere in between those two extremes, all in the pursuit of trying to build our intelligent systems to be even more intelligent. We'll see you next time.